see a lot of people joining now. As I said, we're just going to give other people just a few minutes to grab a cup of tea or something and then join us before we get started. But good to see everybody. First webinar of the year, so Happy New Year. Okay, I'm going to kick things off because we have some really great presentations coming up and I want to maximize the time for questions. But hi everybody, as I said, this is the first UG2 webinar for this year, so Happy New Year. Welcome back. I hope everybody had a great and hopefully relaxing time off for the holiday season. This is the 23rd webinar in our series and a really exciting webinar that we have planned, focusing on hurricane gliders. Really timely because we've just come out of the US hurricane season. So this is perfect timing for us to have this, this presentation. Next slide, Cassie. As always, I like to just give a shout out to the steering committee that continues to work behind the scenes tirelessly to move the mission and aims of UG2 forwards. And I always like to have them on the slide as well, particularly now as we are moving forward workshop planning. They are very busy and dedicating a lot of their time to help with planning for that workshop. So a huge shout out to all of them. Really appreciate the work that they're doing for UG2. Next slide. So just a brief agenda so everybody knows what to expect. I have some very exciting updates to give you from the UG2 side. Lots of events coming up in the next few months. So I'll briefly present on those. And then we'll move into the presentation section. We have 3 fantastic experts with us to present on hurricane gliders coming out of that season. And excuse me, and we will be holding all questions until the end. So have more of an open sort of Q&A discussion section after the 3 presentations. And then I'll do a very quick wrap up if there's time. But again, my hope is just to maximize as much time for all of you to ask your questions whilst we have these 3 folks in the room for us. Next slide. So just some brief updates from me. As many of you, excuse me, as many of you know, we've got the Ocean Science meeting coming up in just a few weeks. And UG2 will be presenting a town hall. We're running this in collaboration with the European group. And we are looking at underwater gliders in action with a focus on ocean emergency preparedness. So this webinar is also a really great presentation to sort of act as a prelude to that town hall. So for those of you that are coming to Ocean Sciences, please do come and find us on the Tuesday town hall session. I've put the details there. We will also share this on the listserv that we have for everybody and via UG2 Slack so everybody knows where we'll be and where to find us. But that should be a really interesting town hall, and I really encourage you all to come. It's a great sort of collaboration effort between the European group and then us in the US. The next thing just I want to flag, those of you that are signed up to our newsletter and mail serve will be receiving the UG2 newsletter. The second edition came out just before Christmas. and the next one is due to come out in July. As always, if anybody has anything they want included in this newsletter, so publications that have come out, upcoming job opportunities, events, and so on, or has somebody that should be featured in our sort of spotlight section, please do send me an email, let me know. And as I said, that's scheduled for July, and then the next one will be December. Next slide, Cassie. So my biggest update is that we are busy, tirelessly working now behind the scenes to plan the upcoming UG2 workshop. So this workshop will be in May, May 18 to 20, and we're working with the team at USF St. Pete, so Florida, and we are planning 3 action-packed days for everybody. Lots of really great breakout sessions being planned, from data management to international partnerships. We've got early career events being planned. There's grant writing sessions. There's also several sessions dedicated to pilots and operations, and some living resource sessions. So yeah, really varied. This will be run in a very similar format to the workshop in 2024 in Michigan. So technical workshop, keep everybody busy, and a variety of different formats, from presentations, posters, some more open community discussions and breakout sessions. So some key dates. We have just about a month until registration closes. So you can use that QR code. You can also access registration links via the website and via Slack. March 15th is a deadline for registration and abstracts. It's also the deadline if anyone needs some travel support in order to attend. I do encourage you to register as soon as you can, and submit your abstracts. We will start reviewing those abstracts in mid-March, end of March. If you have any questions, please don't hesitate to reach out to me, either by the email there or my email, I think it was on the last slide as well, or reach out to me by Slack. I really encourage you all to register as soon as possible. There's also information on the website for the hotel block that we have. It is a limited hotel block, so we have a limited number of rooms available at the Hilton. So again, if you are planning to attend, I do encourage you to reserve rooms and everything as soon as possible. Any questions, please reach out. Really looking forward to seeing you all there in May. Next slide, Cassie. The last thing I just want to mention is that, as always, we do rely on the generous support that we receive from our partners in terms of sponsorship. We have some really exciting sponsorship opportunities available for this workshop. Slight change from our usual setup, but a great chance for anyone to get involved. So any academic institutions or labs, industry groups, and so on that wish to come and participate, or also exhibit. We've got spaces there for industry exhibitors. And then something else we have this workshop is the chance for groups or institutions to support workforce development and actually sponsor a student or a technician to attend. So some great opportunities to get involved, and have some logo placement and so on. If you're interested, again, please just reach out to me, and I'm happy to coordinate any of that with you. Next slide. Okay, that's enough from me. If anyone has any questions about the workshop or anything, feel free to pop them in the chat and I can address them later as well. But I would like to move straight into these presentations. And as I said, we've got 3 great presenters and experts with us today to talk about hurricane gliders and all the excitement that they bring. So I will first introduce Dr. Emily Landeen. Emily is the lead for the IOOS-led Hurricane Glider Coordination Team. Prior to this position, she was a management consultant and provided professional guidance and implementation support to numerous private, academic, and federal institutions to improve their performance, solve complex problems, and maximize growth. So I will hand over to you, Emily.
Thanks. Okay, can everybody hear me and see my slides? Okay.
Yes.
super familiar with Zoom. We usually use Google Meet, so if something happens while I'm presenting, just feel free to interrupt me. But thank you, Georgia. And hi, everyone. Glad to be here. Scott and Matthew and I are all excited to kick off the 2026 webinar series. And I am excited to tell you about the IOOS-led Hurricane Glider Coordination Team and the 2025 hurricane season. So first, why hurricanes? Hurricanes are responsible for nearly 53% of the nation's billion-dollar disasters and have caused over $1.5 trillion in damages and over 7,000 deaths in the US. And improving decision-making on the ground before a hurricane makes landfall is essential to ensure that preparations and evacuations and deployment of first responders occur where they are most needed. That requires local governments and decision makers having access to timely and accurate hurricane forecasts so that they can make the most informed decisions to best protect life and property. However, one of the challenges with providing decision makers with accurate hurricane forecasts is that while hurricane track forecasts have improved significantly over the past few decades, hurricane intensity forecasts have only seen marginal improvements. So we know where a hurricane's going to go, but we don't always know how strong it's going to be when it makes landfall. One of the reasons that hurricane intensity forecast error has only shown marginal improvement is the poor representation of oceans in forecast models. So we all know that the ocean influences a hurricane's strength. The ocean's temperature, the heat content, provides the energy for a storm to rapidly intensify or weaken. And there are also essential ocean features that we know play a critical role in a storm's intensification or weakening. These features have been challenging for forecast models to get right because they are inherently dynamic in nature and because of limited ocean observations that are available to characterize these ocean features. So of course, one solution is to gather more real-time in situ ocean observations so that we can improve ocean representation in models. And studies have shown, including studies by Matthieu, who's going to tell you more about this in a few minutes, that correctly initializing the ocean and correctly in representing these essential ocean features in NOAA's experimental coupled forecast models can reduce hurricane intensity forecast error by up to 50%. That's where gliders come in, because gliders are uniquely capable at collecting these critical in situ subsurface ocean data that are required to better represent the ocean in numerical models to resolve these dynamic ocean features. And because they are autonomous and they can travel where it may not be safe for people or ships to go, gliders can show how the upper ocean responds both before, during, and after a storm passes. It's important to note that when we say hurricane gliders, we do not mean that these gliders chase a storm. So if a hurricane is forming in the Atlantic, our pilots do not quickly pivot and change course and start driving their gliders towards that storm. No. The best way that gliders contribute to improving forecast is through long-term, sustained monitoring of the ocean ahead of a storm's response, ahead of a storm's approach. Since 2018, IOOS has led the coordination of nearly 30 partners each hurricane season to operate gliders in coastal US and international waters. Every glider collects subsurface temperature and salinity data and monitors these essential ocean features that we know influence hurricane intensity. And for anyone on the webinar today who's not familiar with IOOS, the US IOOS office sits within NOAA's National Ocean Service and works to coordinate regional ocean observations and activities and connect those to the national and global infrastructure through our partnerships, which include 17 federal agencies, 11 regional associations, and the Global Ocean Observing System. So as I just mentioned, IOOS leads the coordination of the hurricane glider team every hurricane season. Once these gliders collect their data, that data is transmitted to IOOS's Glider Data Assembly Center, often referred to as the glider DAC or just the GDAC. The GDAC integrates all of the glider data and makes them accessible to the GTS, the Global Telecommunications System, for use in NOAA's forecasting models and other global forecasting models, and also makes them available for archiving at NCEI. The Hurricanes Glider Coordination Team is comprised of over 30 partners that are spread across the Caribbean, the tropical Atlantic, the mid-Atlantic bight, the South Atlantic bight, the Gulf of America, Pacific Islands, and international waters. It is a team that is constantly learning and evolving, and we had new partners joining us last year, which is always exciting. It's a really fantastic, dynamic group of operators and scientists, and I know many of you are joining us today on this webinar. It's nice to see so many friendly faces. The main objective of the Hurricane Glider Coordination Team is to collect targeted and sustained surface and subsurface ocean observations throughout the hurricane season. With these observations, we aim to help improve the representation of oceans in coupled hurricane forecast models to ultimately help improve hurricane intensity forecasts. There are also many secondary objectives that the team realizes, such as improving our understanding of air-sea fluxes during hurricanes, conducting research that assesses the impact of glider data, which Matthieu is going to tell you more about in a few minutes. And we also work with other NOAA partners to improve the co-location of ocean and atmospheric systems during hurricanes. So this graphic in the upper right shows that gliders are only one part of the many observing systems that NOAA deploys to gather atmospheric and ocean data each hurricane season. And NOAA has been working to better co-locate these observing systems. And I'm going to touch on this more in a few minutes when we talk about Aaron and why NOAA is making such a concerted effort to do that. One particular partner note that I want to mention is the Navy. The 2018 CNO legislation mandated NOAA to coordinate autonomous maritime systems with the Navy. And since then, the Navy has provided gliders each hurricane season. These gliders provide about 25% of all of the cumulative Atlantic glider observations that are delivered to NOAA each season. The Navy has been a really wonderful partner to our team. They help us fill gaps in ocean coverage that may not otherwise be able to sample. And we're going to see that when we get to, when we see the tracks for where our gliders flew this past season. Okay, so now let's look at the 2025 hurricane season. The big headline for this year was that for the first time in a decade, no hurricane made landfall in the US. If you're a hurricane person interested in hurricanes, this was surprising, but even though we didn't experience any landfalling hurricanes in the US, that doesn't mean the season wasn't active, and it certainly didn't mean that we learned a lot from glider operations, because we did. So if we look at just the Atlantic Basin, which includes the Caribbean, the Gulf of America, the South Atlantic bight, and the Mid-Atlantic bight, we see that activity in the Atlantic was nearly spot on from what NOAA predicted. The Atlantic had 13 named storms, 5 of which became hurricanes, 4 of which became major hurricanes, and we had 3 Category 5 hurricanes in the Atlantic. 2025 is tied as the second most number of Category 5 storms on record in the Atlantic. The only year that saw more Category 5 storms was 2005 when there were 4 Category 5 storms. So there was a lot of activity in the Atlantic in the last year. Okay, so if we look at our glider operations in the Atlantic for the last season, I just want to back up and quickly reemphasize that our team does not chase gliders. We plan and coordinate glider deployments well ahead of the hurricane season. So every year, each glider operator submits their deployment plan. So we know ahead of time where each glider is expected to fly. So our glider operators are thinking ahead of time, like, where in the ocean do we want to deploy to provide the most valuable ocean data? What ocean features are we going to target for data collection? So here in this figure, we're seeing the 2025 deployment plan. The Navy gliders are shown in this yellowy gold color, and our NOAA and partner gliders are shown in teal. And then if we look at the actual tracks for where the gliders flew last season, you can see that these two maps really are well aligned. So really quickly, if you look at the deployment plan, there were 3 Navy gliders that were targeting the loop current in the Gulf, and we can see them in the glider tracks that they're really well represented. Around Puerto Rico, we had 1 Navy glider flying north of Puerto Rico and 2 south, and we can see that here in the glider track map. And then in the bottom right, we can see the deployment plan for Rutgers Barbados glider, which Scott is going to tell you about more in a few minutes, and we can see where that glider flew in the glider track map. So the team works to coordinate glider deployments well before the start of hurricane season in June. And if we look at the numbers for the Atlantic season, overall, there were 73 total glider deployments. These gliders flew for a cumulative total of 3,466 days at sea and provided over 86,000 data profiles to the GTS. Okay, turning to the Pacific, again, we can see that the activity in the Pacific was really closely aligned with what NOAA predicted. And if we look at glider operations, I'm not showing the deployment plan for the Pacific, but these glider operators do provide their deployment plans ahead of time. But in the Pacific, there was a total of 6 glider deployments. Those gliders flew for a total of 466 days at sea and provided nearly 4,500 data profiles to the GTS. One highlight from 2025 was really international glider operations. We had a record number of international glider partners and gliders flying in international waters that were providing their data to the GTS and the glider deck. So there were 15 total international glider deployments. These included gliders in Mexico and Barbados, the Bahamas, Bermuda, and we had a German partner who was flying a glider north of the US Virgin Islands. These international gliders had a total of 15 total deployments. They flew for 1,100 days at sea and provided over 14,000 data profiles to the GTS. That was a lot of numbers, I know. If we look at the entire season for the Pacific and the Atlantic for all the gliders that were part of our partnership, there was a total of 79 deployments. Those gliders flew for a total of 3,932 days at sea and provided over 90,000 data profiles to the GTS. Okay, I just want to highlight a few, touch on a few highlights from last season, mostly Hurricane Erin. I really want to emphasize Hurricane Erin because this storm exemplifies the important work that the Hurricane Glider Coordination Team does and how the ocean data that the gliders are providing are becoming more integrated and recognized and valued across NOAA. Hurricane Erin rapidly intensified within 24 hours, going from a tropical storm all the way to a Category 5 storm. And during that time, we had 3 gliders in the path of Hurricane Erin. We had a Navy glider, an AOML glider, and our German partner Herion had their glider called Echo also in the path. Here you can see on the right a blown up image of the eye of Hurricane Erin when it was a Category 4 storm, and you can see Herion's glider Echo right there in the eye of the storm. So our team had 3 gliders in the path of Erin as it was rapidly intensifying. continuously gathering data and transmitting that data in near real time to NOAA scientists and allowing them to understand how the ocean was behaving both during and after this period of rapid intensification. And these are some of the data that those gliders were provided, or these are a snapshot of data that those gliders were collecting during that period of rapid intensification. Matthieu and Scott are going to go into a little bit more detail about what these glider data show and how they helped keep NOAA's ocean models on track. But what I'm showing here really quickly is that these gliders are showing in near real time that the ocean was cooling under Erin as the storm passed over them. Another really big highlight from last year was that those same gliders were included in the National Hurricane Center's discussion of Erin. So for every named storm, the NHC provides hurricane discussions which summarize how a storm is acting and how they expect the storm to continue to behave. And here, the NHC called out and noted that several gliders were near the inner core of Erin over the past 24 hours, and their in situ observations indicate that Erin has already cooled in the waters in its vicinity of up to 1 degrees Celsius over the past day. This is a big deal. This was really exciting for the team to see because it shows that across NOAA, across the line offices, and across all of the programs, glider data are really being recognized and valued more and more for their ability to show how oceans are behaving under a storm. And it's also showing that meteorologists are recognizing more and more the importance of glider data and understanding the important role that oceans play in storm behavior and the need for them to better understand ocean features so that they can better predict how a storm is going to evolve. So this was a really exciting highlight from last year. Okay, another really fun highlight from Hurricane Erin. I'm going to show you a video that was shared on the Weather Channel on August 25th. This is going to show, you're going to see Hurricane Erin passing through the Caribbean, and you're going to see all of the different observing systems that NOAA had in the path as it traveled. It's going to go really fast. I'm going to narrate it, and then we're going to look at it in a little more detail. Okay, so here we see a Hurricane Erin passing. We can see a Hurricane Hunter airplane come in really quick. You can see its path where it's flying. Right there in the center are 3 gliders covering. You can see a variety of moorings and drifters in the area. We're going to keep going. Same Hurricane Hunter airplane deploying. And then as it nearly ends, whoop, right there in the corner, we have a 4th glider that we had that was also in the path of Hurricane Erin. So this was just really fun to see our gliders represented on the hurricane, on the Weather Channel, and just noting how important representation of different observing systems and gliders and ocean data are as we continue to try to improve hurricane intensity forecast. I know they're really fast. It's a little bit hard to see. So this is a screenshot from that same video. And I think you all should have access to these slides. So if you want to watch it slower, just kind of look at it in a little more detail, you have access to that. But I'm just going to point out what that showed is that here in the center of the image, you can see the gray circle is the eye of Hurricane Erin. And right in that center, we have our 3 gliders, the Navy glider on the left, AOML glider in the middle, and the Harrion glider on the right. We can see that there are a variety of moorings and drifters in the vicinity. And then you can see the path that the Hurricane Hunter airplane took to drop 3 dropsondes. These dropsondes were specifically deployed to target the 3 gliders that were underneath Hurricane Erin. So as I mentioned before, NOAA has been working to improve the co-localization of observing systems because this provides a more complete picture of the atmospheric and surface ocean and subsurface ocean dynamics occurring during storm, which provides scientists the opportunity to understand the co-evolution of both the ocean and the atmosphere during a storm's passage, and ultimately will help improve hurricane intensity forecasts. And I really want to specifically highlight GOMO and AOML for this effort. So Cheyenne Steinberger, the lead of GOMO's Extreme Events Program and Chaos Experiment, and Lev Looney at AOML have both worked to facilitate the co-localization of these systems and have been doing really great work with this. Okay, that's all I have. That was a quick highlight and overview of our team and the 2025 season. I just want to say thank you all for inviting me to be here and listening to what we have to say. If you or one of your partners is not part of the Hurricane Glider Coordination Team, but you want to join us, please feel free to reach out to me. I will make sure that you get added to our email list and the meeting invites. If you are not sending your glider data to the IOOS Glider DAC, but you want to, we would love to have you join us so that we can leverage your data to help improve hurricane intensity forecasts. So if you need more information about that, feel free to reach out to me or the Glider DAC team. And with that, I will just say thank you again. And I will turn it over to Georgia to introduce Scott.
Thank you so much, Emily. Yeah, we're going to, as I said, we'll hold all questions to the end. So we'll move straight through to Scott. It's a pleasure to introduce Dr. Scott Glenn. Scott is a distinguished professor at Rutgers University. His research career spans over 30 years, focusing on implementing sustained real-time ocean observation and forecast systems, and includes the development of new autonomous ocean observing technologies and their application to scientific research in remote and extreme environments, as well as the demonstration of new educational paradigms. I will hand over to you, Scott.
Thank you, Georgia. And here's just a quick intro slide. What we're trying to do here is increase the international collaboration. We're going to take the lessons learned and demonstrated, the approaches, our infrastructure, our successes demonstrated through the IOOS Hurricane Glider program and expand them internationally. And we're doing that within the framework of GOOS. So we want to use that international group. We're doing it as a co-design process where we're working with the international communities together. And this is the tropical cyclone exemplar that I co-lead with Cheyenne Steinberger, who was talked about before. So I bring in the IOOS experience. Cheyenne brings in that OAR GOMO experience. And together we work within GOOS to get better data for our weather service partners. So many groups in NOAA working together. And as a result, we've made many friends. The next slide is shows many of those friends there. There's that IOOS Hurricane Glider group there, about the fourth one down, talking about the coordination, the data flow that Emily talked about, but also the model data comparison products that we produce in real time. That's something that I'll talk about more in this talk. And I want to focus our talk today on the Barbados glider deployment that's illustrated over there on the right-hand side, where we use the small boats, a dive boat in Barbados, in partnership with CIMH, the Caribbean Institute of Meteorology and Hydrography, to deploy this glider in a very important part of the Caribbean that has been so far very undersampled. Next slide. We're doing this to improve the ocean models that feed into the hurricane models. And so the ocean models that assimilate the data are there in the top row. These are the global models. The middle one there is the NOAA RTOFS, the real-time ocean forecast system. This is the one that provides the hurricane models in the row below, their initial and boundary conditions. The couple models are shown on the bottom row there. The main operational one is way over on the right. It's HAVS, that hurricane analysis and forecast system. But the legacy models, HMON and HWRF, still add value, and so they're still run. So all three are kind of being used. And we compare our NOAA models that are feeding these hurricane models with the other global models that are available through the Navy, their Earth System Prediction Capability, the ESPC model, also the European Copernicus system, to get an idea of where the models look similar and where they look different. And so our job then is to improve RTOFs. How do we make it better? And when we talk to the Weather Service, specifically the Environmental Modeling Center. If you could just click once, um, Emily, there you are. There's the EMS feedback that we got, EMC feedback, that RTOFs is limited by what they called a dearth of subsurface profile data. So there's a lot of data in the atmosphere. There's, less data of the ocean surface, but at least there's satellites in space. And there's even less data below the surface. So that subsurface data is critical for us. So that's what we want to improve and get that data in the right place for the Weather Service people. Next slide, please. So we're not the first the only ones to notice this. The World Meteorological Organization has also noticed the importance of these subsurface profiles, and they have this impact workshop once every 4 years. It's the quadrennial workshop where they bring everybody in. So this was their 8th workshop, and it was the first time oceanographers were invited into the room. And here's some of the conclusions of that when the oceanographers are there. That first recommendation is to observing network operators worldwide is that we need to sustain these routine observations of ocean temperature and salinity profiles. And the examples they use are Argo and gliders. We know we need that data in the models to improve them. They found that through their testing, having that ocean data in there was equivalent to one full update cycle of the European system. And so those update cycles of the European system are quite expensive, and you get one for free if you just add in an ocean. They talk about metrics of skill. We're going to look at some of the metrics of skill we've developed within IOOS to look at this and improve what we do, and continuing to work together with the global communities, the IOC for GOOS and the WMO for early warnings for all and to improve these forecasts for the benefit of the people. So the next slide. So here's some of the products that we produce through the IOOS Hurricane Glider program. These are the model data comparison, and there's quite a lot of them that we produce on a regular basis that we're always generating, putting on a website so that anybody can look at it. It's kind of a complex website, but we have solutions for that too. We do the model nowcast maps. So we compare all the models. There's on the right, there's a comparison of RTOFs on one side and the Copernicus system on the other in the Caribbean. And you can see that there's differences in the models. In this case, the salinity, the subsurface salinity is quite different. This is one of the bigger errors that we've seen in the model systems that we have. So we produce all these images to compare where the models are doing similar things, where they're different, and we can use that to help target where the gliders go to get the proper essential ocean features in the models that are feeding the hurricanes. We also do the temperature and salinity profile comparisons, as are showed over there in the middle on the right. That's where every single profile produced by a glider or an Argo system, as recommended, are compared to the 3 operational models. So we can see how those models are doing. In this case, red is the RTOF's model and blue is the glider data. And you can see there's a bit of a bias in terms of a cold and fresh bias that we know about in the model. So we try to correct with the glider data. The third bullet there is, okay, we do have a website that has all those, but it's kind of only, the website the creator can love. Thank God we have Gandalf, Bob Courier. Thank you so much for taking those images and putting them on Gandalf so they can be shared with a broader community. That has really increased the value of what we do and getting it out there and getting feedback to us. And so we keep building this community of informed people who are looking at the models and trying to make them better and trying to decide where they steer their gliders to do that. And as a result, of all this, we produce regular curated slide decks. On a weekly basis, we brief the glider operators as to where important features are, where the models are doing good, where they're not doing so well. And we pass that on to EMC so that they can make improvements in the model. And they use that in their validation studies to make those improvements, across the region. So the next slide. So one of the questions is why the Caribbean? Why are we so focused in GOOS on the Caribbean as a place of importance for us for our pilot studies? And here we've plotted all the hurricane tracks since 2020 in gray. And what we've done is we've turned them red 5 days before U.S. landfall, because that's, the current, you had a 5-day forecast, right, for the hurricanes. And you want so you can prepare. And if you look at where those hurricanes are 5 days before U.S. landfall, um, a lot of them are over the Caribbean. And so if you want to get a good forecast of what that hurricane is going to do, you have to have a good forecast over the Caribbean, which means you have to have a good Caribbean Sea in your model. And if you want to go to a longer lead time, how much lead time did I have for Sandy? For Sandy, for us to prepare for that hurricane, we had 7 days warning. We got that 7 days warning though from the Europeans. How do we get the US up to 7 days warning also so that people have time to react? If you look at the next slide, Emily, there we go. 7 days, even more of the Caribbean is covered. So this is an important region for us. It's hurricanes are an international issue, no matter where you live. So let's continue looking at the Caribbean. Next slide, please. Here we compare the Gulf of America with the Caribbean Sea, and look at the size of these features and what gliders and Argo profiles are deployed in each one. If we look at the Caribbean, compared to the Gulf, Caribbean's twice as big, but it has half the Argo profiles and less than half of the glider profiles in it. And if you look where those profiles are situated, like in 2024 when we were planning this, uh, there's a lot of coverage in the US areas around Puerto Rico, the Virgin Islands, and there's also coverage over by Mexico, where the Mexican gliders and the US gliders were collaborating in a uh, in a science exercise for the national academies. It's actually before hurricane season. And so there's a lot of area that is not being covered by gliders in the Caribbean. And so what is the impact that we see of the profiles produced by Argo and the gliders in this situation? So the next slide. This is where we look at our metrics. And one of the important metrics for hurricanes is ocean heat content. And so the RTOF's model ocean heat content is on the y-axis in each case, and the x-axis is either Argo profiles or the glider profiles, the ocean heat content metric for every single profile that was produced in that time period. And if we look at the Argo profiles, especially at the high ocean heat content, you see that cold bias of RTOFs, the cold bias in the model. And so every time, once every 10 days, that Argo profile surfaces, it has to make a big correction to the model. The model has a long time to drift, but Argo has a climate mission, important climate mission that we can't impact. And so they're there. They have to do that 10-day surfacing. And but it has a big impact on the model. You're hitting it with a big hammer. If you look over at the gliders, because multiple profiles are collected every day, it's assimilated every day. So profiles are provided at the frequency that they're being assimilated by the models. You're nudging it a little bit daily, every day, one after another. And so you're getting a much better solution. You're keeping the model on track without having to make big corrections once every 10 days. So there's a lot of reasons why we have weather-based gliders and climate-based Argo profiles as a really complementary observing system in these areas. Next slide. So now if we move on to what we did in 2025, there's the US area around Puerto Rico and the Virgin Islands and Dominican Republic, and we've been occupying since 2018. Matthieu will talk more about that region over there. Over in Yucatan, there's the 2025 Mexican gliders that were in that area. I'll be talking about those at Ocean Sciences in 2 weeks. And so today I'm going to talk about the 2025 Barbados deployment. What we're trying to do here is capture the Caribbean through flow. We get the inflow from the north with those gliders up in the US waters. We get the inflow from the south along with the Amazon River plume by the Barbados gliders, and we get the outflow by Yucatan with the Mexican gliders. So we're trying to capture that entire through flow with this array from 2025. And then sprinkled throughout that are the Argo profiles. Okay, so next slide. This is the track of the that Barbados hurricane glider that was deployed from there. Joe Gradone was the pilot. I think he's on the call there. We left Barbados. We went out through the Barbados waters into international territory, came back in and out through Guyana, in and out through Trinidad and Tobago, and then zigzagged back and forth across the strong current that was heading into the Caribbean near the end of the mission. 2,000 kilometers total, 3 months at sea, 1,200 profiles contributed in this region where there were no other gliders operating during our history of the hurricane glider program. So the next slide. Here's some of the results that we did expect to see. If we look at the profiles of temperature and salinity over there before the gliders were assimilated. Blue is the glider data from that Barbados glider, and red is the RTOF's model that shows that cold and fresh bias of the subtropical underwater. That subtropical underwater, that's the global conveyor belt that's flowing in from the South Atlantic up into the Caribbean. And we see that cold bias in the model. If we show the next one more click, here's after several days of that glider being out and the assimilation taking place. You see that the models are pulled into compliance with the data. They get closer and closer to that. And this, it's very well illustrated with the subtropical underwater because there's such a big difference in it. And so the glider data, it's being assimilated, it pulls the model into compliance, and this is what we expected to do. But that's just where that glider is deployed. How does that impact the rest of the model spatially? Are we just impacting that one area? And this is one of the big illustrations that we were able to do with the Barbados gliders, as there was only one there in an area of a high need. So the next slide, Emily. This shows a map of that subtropical underwater, the temperature at 150 meters. You see very cold biased water in the south that's coming in to the Caribbean from the South Atlantic. But up around Puerto Rico, we see that very nice warm eddy with 4 Matthieu's gliders in it. So all those gliders are in there correcting those temperatures up and reducing the bias, bringing it into line, and that water circulates around the eddy and it keeps recirculating and they keep hitting it. They keep that area on track with those 4 gliders south of Puerto Rico. The next slide. So this is what happens after several days of the Barbados glider being out there. Not only is that warm water affected right at the glider, the improvements made there. Those characteristics are there advected downstream and to the north. And now we see that warm water is impacting all the Caribbean, well, maybe 2/3 of that whole island chain of the Lesser Antilles there. So helping all the different islands in that area. And so if there were more gliders there, that would probably be even more helpful, where we could start to keep that area on track. If you click it once more, you can see those currents that we were experiencing during that time in the gray glider track there. So that glider south of Barbados, those corrected water characteristics are then being advected at the beginning and up along the island chain. Later in the mission, it was being advected through the island chain. And so this is the correction that we see. And we look at that and we go, well, how many gliders do we really need? We go, well, our eyes are telling us 1, it's doing a good job, but maybe it's not enough. 4, maybe that's pretty good. That's the kind of thing that Matthieu does. They check that mathematically. So Hyun-Suk Kim is doing all those OSE experiments and is coming up with something like, well, maybe we need 4 gliders in the area around Barbados. So what are we going to do next year? The next slide. This is where Joe Gradone comes in with his Schmidt Ocean Institute cruise, where he has a boat out there for a month east of Barbados, with a whole international community coming together to work in that area for looking at mixing and staircases in the area. But if we look at the things that he's bringing on board, the next slide, there it is, 4 gliders. So we don't know the exact answer yet, but it's going to be somewhere around 4. It's going to be really helpful for us in that area. We know that. We hope to have 4 gliders in the area this coming summer during 2026. This is not the only research vessel that'll be out there. We just had the discussions with the group from New Zealand that is going to bring another one on the inside of the Caribbean. And so we'll continue putting these gliders out there during the hurricane season and testing out what kind of observing system do we really need for this region. So my last slide is the next one. For my last slide, some conclusions of how we're building this international community, especially in Barbados, where we're starting from scratch, really. We have technicians coming in for training. They do the MTS, Marine Technology Society Glider School that they have there. We bring the gliders down. We'll bringing them down again in July to do the scouting for that Falcor mission that'll go out. That'll bring that international team of scientists with more gliders for the coordinated sampling. We can see how that does and how that does to improve our models in that area. And we'll continue this hurricane season monitoring in the area. Our vision is to expand what we were doing with the IOOS hurricane gliders to the international community here, and we'll have these glider missions running between multiple Caribbean glider ports, like along the Antilles there between the U.S. Virgin Islands and the Barbados glider port. It's only 1,000 kilometers. We can do that. We can do 2,000 with these deployments. And that vision is for a Caribbean glider fleet. It supports the broad range of IOCRIB needs. I know IOCRIB is a contributor to the U.S., to the UG2 group, so we'll hopefully contribute to their broad needs. But we also provide this data-rich environment that a lot of young scientists from the Caribbean are using for their science theses and stuff, so that we'll be increasing the not only the amount of data that comes in, but also the workforce that's available to do this well into the future. That's it. That's my talk. Thank you, Emily. I'll pass it on to Georgia, who will introduce Matthieu.
Amazing. Thank you so much, Scott. It sounds like it'll be a very busy but exciting year for you all. Our third speaker today is Dr. Matthieu Hénaff. Matthieu is a research oceanographer with NOAA's Atlantic Oceanographic and Meteorological Laboratory, or AOML. His research focuses on improving understanding of how regional ocean dynamical processes affect the other components of the Earth system. It has a wide range of applications, from observing array design to pollution transport, ecosystem protection, boundary currents, marine mammal assessment, and hurricane forecasts. So I will pass it over to you, Matthieu. Thank you.
Thank you, Georgia. And can you see my screen?
Yes, we can see you and hear you well.
Excellent. And so, yeah, I wanted to continue, mention some scientific results and echoing what Emily mentioned earlier, that we deploy gliders to better understand the ocean hurricane interactions and how the ocean respond and might affect hurricanes, as well as how collecting ocean observations with gliders impact hurricane forecasting. So I want to start with some early results that we collected, that we gathered with our first deployment at AOML that they did back in 2014. And that was Hurricane Gonzalo, that was north of Puerto Rico. And we measured with the glider a low salinity layer at the surface of the ocean that you see here. And it was associated with a barrier layer. That's a case in which the haline layer and the thermal layer have different depth, different thicknesses, so that you see on the right here, you have a very shallow haline layer and a very thick temperature layer, and that's what you define. The difference in the depth between those two layers is what you call the barrier layer, and that's that's an obstacle to mixing, and that makes mixing more difficult, and that potentially impacts hurricanes. And that's what we typically see here. You see that even though the haline layer was completely eroded by the passage of the hurricane, in the difference between the blue and the red line, the temperature drop was very limited. It was less than 0.5 degrees Celsius. So most likely the barrier layer suppressed that cooling, and that means that the temperature didn't decrease much when the hurricane was passing, and potentially the hurricane kept being intense or kept intensifying. So this one example is really of value to encourage our community to improve our knowledge of ocean response to tropical cyclones and how this ocean response can feed back onto hurricanes. And that also encourages us to collect data to improve hurricane forecasting. And if we move fast forward to 2025, so those are results from Hurricane Erin that Emily mentioned. And we see there were, like Emily mentioned, 3 gliders next to each other measuring the ocean when Erin passed. And so those are results from 2 of these gliders, the time evolution of temperature and salinity from two gliders that both showed a pronounced cooling of 1 to 2 degrees Celsius. And that information was used directly by forecasters at the National Hurricane Center. And they said, wow, it's cooling more than we expected. Therefore, probably the storm is not going to intensify as we first thought it would be. And they adjusted their forecast. But I also wanted to point out that the glider NG783 at the top row presented a low salinity layer before the storm that was also eroded and mixed with the rest with the water column as the storm passed. So that looks like quite comparable to Hurricane Gonzalo, but in this case, the cooling is much more pronounced. So what happened? Well, the glider in the case of Hurricane Gonzalo was located further away from the center of the storm, and here it was right near the center. So most likely the mixing was more efficient there. So, even though we have that one example from 2014, we still need to collect more data to have a more complete view about how the ocean reacts to the storm, depending on where you are, which quadrant of the storm, closer or further away from the center. So I think this is, we still have work to do. Another case in 2025 in which our glider data were used by forecasters is during Hurricane Melissa. We see on the right the track of Hurricane Melissa after it devastated Jamaica. It went northward and it came over an area that was sampled by one of our gliders deployed east of the Bahamas. You see in the tiny map here. And so that glider was in the area affected by the hurricane here, as you can see. And NHC forecasters looked at glider profiles and noticed that there was a thick layer of warm water near the surface that would be difficult to mix, and that's a lot of heat available for the storm. And based on that information, they adjusted their forecast to a slightly more intense and re-intensification of the storm, which is what was observed. Now moving on to the forecasting aspects of it through modeling. So I'm going to present results from 2017. That was a very busy hurricane season, and especially with Hurricane Maria that devastated Puerto Rico in September 2017 with about 3,000 fatalities and billions of dollars in damages. In that year, there were actually 3 hurricanes that passed in the Eastern Caribbean region, Irma, Jose, and Maria, and they all reached their peak intensity while traveling over that part of the ocean that combines 3 essential ocean features. So it was an area with warm sea surface temperatures and also a large tropical cyclone heat potential. So that's the amount of heat that is sitting at the upper ocean for all waters above 26 degrees Celsius. That's a threshold for hurricane intensification. And finally, this region was affected by low salinity river plume. And we had 3 gliders deployed in that region in 2017 to survey this area. So we performed numerical experiments, ocean observing system experiments using an ocean model here, HICOM, with a data assimilation system. And we assimilated different combination of ocean observations to look at the impact in how the ocean is represented based on what observations you feed the model. And then we added to this ocean OSs what we call coupled observing system experiments, and this time it's using a hurricane forecast model. Here is the HWRF system coupled to the high commotion model, and it has the same, it's used to examine, it uses the outputs from the ocean OSs that I just mentioned as initial conditions for the hurricane predictions, with everything else in the hurricane model being the same. So all the differences that you see after you running the hurricane model are due to the differences in the initial conditions. Therefore, in the differences in the ocean observations, you feed the model. So looking at some of these experiments, first in terms of the ocean model itself, what is the impact of ocean observations? So here I show maps. On the top is maps from the case that doesn't have any ocean observations, and at the bottom is the model that assimilates ocean observations, and on the left is the difference in sea surface temperature with respect to observations, and on the right is the difference in tropical cyclone heat potential with respect to observations. And you see that in the absence of ocean observations, the model is too cold at the surface and has a negative anomaly, not enough tropical cyclone heat potential. But assimilating ocean observations, you correct these errors, and the output of the model is much more realistic. And that translates into the vertical below the surface as well. So that's the time evolution of the vertical temperature compared with a glider that was deployed there. And you see in the absence of observations in the top, you have a cold bias that extends down to 200 meters. But assimilating ocean observations, you correct most of that bias. So really without that assimilation, that model, specific model, was too cold. And how does that translate into hurricane forecasting? So this is the output from the hurricane model. And you see the tracks on the left, and on the right, that's the time evolution of the wind intensity. So in black is what was observed, and in red and blue are two experiments with and without ocean observations. And you see that in red, when you assimilate ocean observations, you reach the intensity that is higher than without ocean observations. Not as high as observed, but you still make progress. And what I found interesting is that the rapid intensification phase of the storm was much better captured when assimilating ocean observations compared to without them. And overall, there's a 25% error reduction in the wind intensity in that case. We also noticed an important aspect is that the enthalpy fluxes, so the energy fluxes from the ocean to the storm in the model, those fluxes were very different with and without ocean observations being assimilated. You see on the left, it's much more intense, which is why you have a more intense storm. That's the process by which the storm gets more intense in the model. We also ran some statistical analysis based on a small ensemble of 6 forecast cycles during Hurricane Maria, and we looked at the root mean square error. So that's the error over the 3-day forecast that covers the time at which the storm made landfall over Puerto Rico. And over this 3-day forecast, when you assimilate ocean observations, there's a 20% error reduction compared to not assimilating ocean observations. And if we focus on the 24 hours before landfall, that's the key time period for forecasters. So then that improvement reaches 30%. And if we look at the details of the contributions from specific observation platforms, altimetry, Argo floats, and gliders in that 24-hour window, because gliders were in proximity of the island, that's when they had the most impact among the platforms. Now moving on to another storm that was Hurricane Michael in the Gulf region, Category 5, also a lot of damage. And we looked at the ocean conditions before landfall, and we noticed that Hurricane Michael interacted with detached loop current eddy that's associated with, it's a warm core eddy, so that's high temperature and high tropical cyclone heat potential. There was another warm core eddy to the northeast of the Gulf. And in addition to that, you had the very large river plume, Mississippi River plume, that is supportive of the barrier layer effect that I mentioned earlier. And finally, there were also warm anomalies in sea surface temperature in the northeast corner of the Gulf. So many conditions that are favorable for intensification. We also had 2 gliders in the region, and one of them was deployed in the Mississippi River plume. And we see at the bottom is the time evolution of the temperature, and on the right is the temperature anomalies with respect to that initial date of that plot. And you see that the temperature didn't move much, even though the storm passed over that region. That's because of the stratification, very strong stratification associated with the river plume. So that prevented the ocean from cooling. There's no cooling at the surface, as you see on the right. We had a second glider deployed in that warm core, smaller eddy that I mentioned earlier. And then the situation was very different. The black line on the time evolution of the vertical temperature is a 26-degree isotherm, and it's much deeper in the warm core eddy. And there you see a cooling when the storm passed, but that warm layer was so thick and the temperature was so high that the ocean stayed still warmer than 26 degrees, and so still prone to support intensification. So really 2 different conditions, even though the gliders are not too far apart. So really the ocean structure and how it interacts with the storm are very different. And now in terms of modeling, we performed similar experiments as the ones I mentioned earlier. We compared here a case with all ocean observations, without ocean observations, and with climatological ocean conditions. And you see here the time evolution in terms of intensity is very different. When you have all ocean observations in red, the storm is much more intense and much closer to the observed intensity, as opposed to a free ocean that is not constrained with ocean observations, or a climatological ocean in cyan. Both cases lead to intensification that is not enough, and that doesn't give a realistic storm intensity. They are limited to category 1 or 2. And similar to the Maria case, we found very big differences in terms of enthalpy fluxes between the cases with and without ocean observations. Now moving on to another of such data denial experiments, observing system experiments. That's the work by Liu et al. During Hurricane Isaias in 2020. And this time it uses the reversion of the MOM6 model that's developed at NOAA and the Marine JEDI data simulation suite. And these experiments looked at the impact of assimilating satellite observations together with this glider data that were located around Puerto Rico and the Dominican Republic, as seen on the map at the bottom right corner. And the coupled OSEs are run with an early version of the HAF system. And what this study found is that the glider data were good at capturing barrier layers. Also, the experiments that assimilated glider data, so that's the map on the right, so that's the 2 plots on the right, assimilating only gliders or gliders together with satellite data. Both cases show an increase in enthalpy fluxes from the ocean to the atmosphere that leads to a more intense storm. And as a result, this study found that ocean observations led to a reduced intensity forecast error of 30%. That's the plots at the bottom. The different experiments showed a better representation of the central pressure and the wind intensity when assimilating ocean observations. And out of this 30% error reduction, half of it can be attributed to gliders. So another strong result. I also want to mention the work done by Corbin Brooks at EMC, who looked at the out-of-ocean model that is used operationally to initialize the hurricane forecast models at NOAA. And he used a night joint model analysis, which allows estimating the impact of observation platforms onto the model. And he found that gliders, he really focused on gliders, and those are maps that showed the impact in terms of error reduction in temperature and salinity of assimilating gliders for the month of August 2024. And all the data taken by gliders have a positive impact on the model. And we also see here that this error reduction is localized in key areas close to the coast where hurricanes are likely to make landfall. So those are critical areas to constrain well in the model from a forecasting perspective. He also looked at the impact on the vertical, and we found that the gliders are best at constraining the temperature between 50 and 300 meters, meaning in the main thermocline, But on the salinity side, the impact of gliders is really more pronounced in the upper 20 meters. That is where river plume, the typical thickness of the Mississippi River plume or the Orinoco Amazon River plume. So the constraint is not exactly the same in temperature and salinity. And finally, compare the impact of gliders with the impact of other platforms. And in terms of impact per observation, that is the plots on the left, so for temperature and salinity. In each case, the gliders outperform all other systems in terms of per glider observation. And that means that gliders are good candidates if you want to improve the constraint on your model because they have a very strong impact. And as I mentioned earlier, the impact is localized in key areas of the domain close to coastlines where gliders can make where hurricanes, can make landfall. And finally, I wanted to briefly mention a sensitivity experiment that we've been running in the case of Hurricane Idalia in 2023. So that's not a data denial experiment. It's more like a feature denial experiment in which we modified the output from the AOML model that is run operationally to remove the Mississippi River plume. And that's what it looks like after we remove the plume by applying a threshold of salinity of 36. So we wanted to preserve the regional differences, not remove all salinity signal, but just the intense one associated with the river plume. So you still have contrast within the Gulf and with the Caribbean Sea, as well as on the vertical on the right, you still see differences in the different water masses below the plume. And how does that translate in terms of hurricane forecasting? So that's the output using the HAFS model. You see on the left are the tracks as observed and simulated, and the simulated tracks are close to the observed one. And now in terms of an intensity, the reference case is slightly more intense, that's in red, compared to the black, the observed wind intensity. And the modified case without the river plume is a little weaker than observed. And in terms of sea surface temperature evolution before and after the storm, the cooling is intense in both cases, but it's more intense in the modified case without the river plume by about 0.3 degrees Celsius. We also had access to sail drone data. There was a sail drone at the surface measuring winds and pressure at the surface and temperature at the ocean surface and currents using a downward ADCP. It was on the edge of the West Florida shelf here. And we first compared the currents in the coupled model, and we realized that the coupled model does a very nice job in representing the current intensity. It compares very well with the observations. And we also looked at the temperature evolution at the surface, and there again, the model is realistic with 31 degrees Celsius at the surface before the storm and a cooling of about 2 degrees that is close to the one that's observed. And you see the difference in the two cases with and without the river plume. It's more intense without the river plume by 0.2, 0.3 degrees Celsius. And now in terms of wind intensity forecast, that's an average over 8 forecast cycles that all cover the whole Gulf, that the lifetime of the storm covered the whole Gulf. And there is a wind intensity reduction by about 10 knots when you remove the river plume. And that leads to a difference in estimated category for the hurricane. So that's a significant difference. These results suggest that the river plume supported the strong intensity of Hurricane Idalia. So this is work in progress, but I wanted to share it with you today. So quickly, take-home messages. I'm going to repeat what Emily said. The ocean matters. The essential ocean features, typically river plume, warm core eddies, impact the evolution of hurricanes. And hurricane gliders are especially good at characterizing these essential ocean features. And as such, they provide essential information for hurricane prediction. And we found that the correct representation of the ocean in operational models leads to reduced error in hurricane intensity forecasts, and that is best achieved by a combination of observations. You need altimetry to constrain the mesoscale, you need profilers like Argo floats and gliders to constrain the vertical structure, and you need sea surface temperature by satellite measurements to constrain the surface of the model. And yeah, the last point is that this year, forecasters from the National Hurricane Center started using our hurricane glider data directly for their environmental awareness. So they have access to our data through the models that they use that are generated at EMC and directly from in situ data. And yeah, that's our contribution, and I think we can all be proud. So thank you.
Amazing. Thank you so much, Matthieu. Okay, so we have time now for questions. So if anyone has a question, feel free to unmute, pop your hand up, and you can ask your question directly, or you can also pop a question into the chat and I can relay that. Nobody has any any questions or comments? I guess I will kick us off with a question. So whoever wants to answer this, what do you oh, actually, I see a hand up, so I will pass that over.
Yeah, hi Scott and everybody. Great talks on this. Do you have an idea of what the cost is for maintaining sort of I mean, you said something like 4 gliders off of the Lesser Antilles and that stuff. I mean, how many months a year do we need to have the gliders out, and what's that cost so that people can think about planning sort of long term, what that might look like if you were doing, say, a bit more in the Caribbean and sort of filling out sort of what you need in the Gulf of Mexico, what that is. Is it, 10 million a year? Is it 5 million a year? Do you have an idea?
So, oh, if you wanted to total it up, I can't do the totals in my head, but we have we know what gliders cost. Like the gliders that we use are the very high-end research gliders, 200K, 300K, because we load them full of sensors to purchase them. How much does a glider mission cost? Typically about 100K. Maybe it's a little bit less if it's close to home, maybe it's a little bit more if it's far away. And so you can add those up as many missions as you want. That was a 90-day mission that we did over there off of Barbados. Um, you know, how many regions do we want to cover? You start adding that up, you you get an idea of what that would be.
Thanks. Just always trying to think about what it is like if we build out and have to go after, I mean, as you have, try to get more consistent funding from other
We
places or other situations and what that looks like.
Yeah, we see that the costs are actually quite cheap compared to like trying to get research vessels out there, and also the improved forecasts. Um, it's quite valuable for that. And so the costs come out to be pretty pretty inexpensive when you talk to about the lives saved and the damages prevented. And there are groups out there, especially foundations that see this as a valuable investment.
Thank you.
Any other questions at this time? I will just also highlight a great point in the chat that Sean said that all three presentations were excellent, so it's hard to think of unanswered questions. But we do have a technical question that's come up into the chat. How do the pilots with the gliders manage to not have problems with drifting sargassum banks during an operation?
Oh, we were snorkeling with those sargassum banks during the deployment of that Barbados glider, and they were everywhere. And even just to take a photo of it, you had to push the sargassum away. And so we've had examples of where that sargassum is there, and the glider still manages to surface through that. Sometimes, well, every time that we had with that Barbados glider and communicate. We've also had gliders that were saved by the sargassum banks when one was damaged and was floating at the surface. It floated up on an island in Puerto Rico on a bank of sargassum and was recovered by the people that were raking the beaches to recover that glider. That was the same one that went in at Barbados, and so uh, they've also helped us in some cases. So sargassum forecasting is another very important reason to have the gliders out there.
Matthew, I saw you unmute as well. Do you have any
Yeah,
comments on sargassum?
I don't have much to add. We don't have problems related to sargassum. I mean, it doesn't affect the operations of our gliders. They're able to go through and go back down. But as of now, I don't know in the future, but I don't think there's much we can do. But so far we haven't had any problems due to sargassum. We have other problems, but not with sargassum.
And then Carl, I'll hand over to you. You said you've got a comment?
Yeah. So, can you hear me?
Yes.
Yes, yeah.
Yeah. So, I worked for the Naval Oceanographic Office. I mean, Scott and a few other people remember me probably, but it's just amazing how many more observations we have. And the thing that struck me, so one comment that was made about the Gulf of Mexico, is when the oil spill hit. I worked in Oceano, and they said, "Carl, what do we got for observations?" That was like late April. Going back to January of that first of that year, one observation profile in the Gulf of Mexico, because evidently the glider or the profiling program hadn't kicked in yet in terms of deploying in the Gulf of Mexico. Well, the other day I'm looking at a thing from I guess it was the Happy New Year thing from the National Academy of Science, and just that one experiment in the loop current area, 10,000 profiles. I said, holy Christmas, how many magnitudes is that in terms of an increase? So that's my comment.
There's been a significant increase in the number of profiles since 2018. So we've been coordinating the hurricane glider fleets. And not only is there profiles from the coordinated fleets, anybody else that's out there doing an experiment for whatever purpose it is, if they just send their data to the glider deck, it automatically goes to the GTS, or they can have it automatically go to the GTS and into the models and be assimilated and improve hurricane forecasts. You know, they get criteria 2 credit for free just by checking a box at the glider deck. So we're really trying to build this community where everybody can contribute, no matter what they're doing out there with a glider. And gliders are just becoming more and more widespread. And then the National Academies, of course, invested in a whole fleet of Argo floats that's been out there. And instead of profiling once every 10 days, as the global climate floats do, they profile once every 5 days because they're in a regional sea. Argo doesn't do the marginal seas, but the National Academies is doing that right now. Someday those research funds go away, and we have to come up with a way of operationalizing all these activities.
Yeah, and you can see too, not just in terms of how often, but like in the Argo program, again, like you said, in inland, enclosed seas, whatever, uh, Red Sea, Sea of Japan, and stuff like that. Sometimes I should say sometimes, often you observe a common maximum depth because there's no temporal or spatial variability below that depth. And so the local people say, not why measure below that depth? It's like 800 meters in the Sea of Japan or something like that. It's like 400 or whatever in the Red Sea. So it just makes sense to make very wise decisions that way.
Thank you,
There's
Carl.
also, okay.
Oh, carry on, Scott.
I was going to say there's also the realization globally that Earth system prediction models are increasingly important, especially for the weather. And the concept of, the global basic observing network for the WMO and then the regional basic observing networks for the WMO. They're increasingly looking at adding ocean variables and ocean profiles to that because those regional observing networks are where they're worried about hurricanes and typhoons, and those are the ones that are in those marginal seas not covered by the Argo Climate Program.
Yeah, I think it's great that these observation tools and technologies are getting more recognition now and awareness. We have just a couple of minutes left. Are there any final questions or comments? I just want to shout out as well that I have shared my email in the chat box with a link to the registration for the UG2 workshop. I meant to say as well that workshop registration is free. There is no cost to attend. And we will also be sharing the recording of this via the UG2 platforms and uploading this also to the UG2 YouTube. So I'll just say there's one more minute if anyone has any final questions or comments. Now's your chance, but these were fantastic presentations, very informative.
We want to welcome the community to join us in 2026.
Yes, I think you all shared different ways that can be done. So yeah, let's definitely make this a busy but great year for hurricane gliders. Okay. Well, it's time to wrap up then. So I just want to say again, a huge thank you to Emily, Scott, and Matthieu for giving some amazing work and effort, not only in the sort of research field and everything as well, but also providing your time today to share this with the community. As I said, we'll be sharing this presentation across the platforms over the next day or so. Hope to see many of you at OSM at the end of the month and also at the workshop in May. So yes, huge thank you and enjoy the rest of your day and week.
Thanks, everyone.
Thank you, everyone.
Thank you.
Thank you.